So, that means our conclusion is there is only one such value of f of pi, which is exactly equal to 2 pi. Fine. Okay. So, now let us go to solving some more problems. First problem, find the value of C or values of C, we do not know how many, in MVT, in mean value theorem, for this function f of x equal to square root of x minus 1, when 1 is less than or equal to x less than or equal to 3. So, what does it mean? You have the function f of x is square root of x minus 1. On this closed interval it is continuous, and on the open interval 1 to 3 it is differentiable. So, you can use mean value theorem on this interval, that is f of 3 minus f of 1 divided by 3 minus 1 should be equal to f prime c for some c. So, that c we want to find, or if possible many c's which will give that value for this f, that is what we want. Okay. So, now f of 3 minus f of 1 is f prime c into 3 minus 1, that is what the conclusion of mean value theorem says. So, we find out what happens f of 3 minus f of 1, at 3 it takes the value root 2 and at 1 it takes the value 0. So, left side is root 2 and right side we have to find out f prime. So, f prime is 1 divided by 2 square root of x minus 1. It is evaluated at c, that is 2 into c minus 1 to the power minus 1, and 3 minus 1 is equal to 2. So, this is the equation we get, which we solve to find our c, that gives c equal to 3 by 2. So, there is a unique value for this function. For different functions there can be other c's in the interval, where the values of the function its derivative are same. Okay. So, let us go to second problem. Here we have a function f of x, which is defined as f of x equal to x for x between 0 and 1 including 0, and f of 1 equal to 0. So, that means f is defined at least here through this on the closed interval 0 to 1. So, at 1 it is 0, at everywhere else it is like identity function f x equal to x. Now, this function is differentiable on the open interval 0 1. So, that is easy to see, because on the open interval it is f x equal to x, and this function also has the property that f of 0 equal to 0, that is also correct because f x equal to x. However, f prime x is equal to 1, where in the open interval 0 to 1. So, it is never 0 on the open interval 0 1, right. So, like in the Rolle's theorem, you have f of 1 equal to f of 0, which of course happen to be 0 here both the side, and f is continuous or it is differentiable, right, on 0 1. So, why it does not contradict Rolle's theorem? As you see, that Rolle's theorem needs that f should be continuous on the closed interval 0 1, but it is not. So, that is the problem. It is not continuous, because when you take the limit of f of x, where from the left hand side you get it is 1, but f of 1 is given to be 0. There is a jump there. So, there Rolle's theorems, one of the conditions is not satisfied, namely f should be continuous on the closed interval, which is not true here. Okay. So, let us go to third problem, which asks to show that between any two zeros of this polynomial. So, suppose this polynomial vanishes at 2 points a and b in the reals. It says that there exists a 0, lies a 0 of this polynomial. So, we have two zeros, say a and b of the first polynomial. It says that between that there is another 0 of this. This is very easy to see if you recognize the second polynomial as the derivative of the first polynomial, fine. and then apply Rolle's theorem. So, that is what we do. Let f of x be the first polynomial, then f prime x is equal to the second polynomial, right. So, Rolle's theorem says that if a is a root, that is f of a equal to 0, that is also equal to f of b for a less than b, then between a and b there is a point c where its derivative should be 0. Therefore, there is a 0 of this between any two zeros of first polynomial. Okay. Fine. So, we come to the fourth problem. So, here it is a physical application. It asks for, suppose the acceleration of a moving particle is a, which is given as 9 by pi square cosine 3t by pi, right, and at any point t. So, its initial velocity is v 0 equal to 0, though it is acceleration velocity are given, we are not really concerned about them as vector quantities, we are taking their scalar parts which are really numbers. So, they will be functions. So, its initial velocity is given as v 0 equal to 0 and its initial displacement is s of 0 equal to 1. So, as you record that v will be equal to s dot and a is equal to again v dot, which is s double dot, that is derivative with respect to t. Second derivative of s will give us v. So, we are asked to find the position s t of the particular time t, that means find the function s of t if these things are given. Okay. So, a is dv by dt, which is given to be 9 pi square cosine 3t by pi. So, if you take u equal to 3 by pi sin 3t by pi, you can see that derivative of u with respect to t gives you that. Does it give? It is 3 by pi times cosine 3t by pi into 3t by pi with respect to t, that gives again 3 by pi. So, that makes up to 9 by pi square. Okay. So, it is the derivative of the function u, but u need not be equal to v. Our corollary to mean value theorem says that u can differ from v by a constant, right. So, we can write v equal to u plus c for some constant c. Now, we will use the condition that v 0 equal to 0. So, that gives u 0 plus c equal to 0, which gives u evaluated at 0 is already 0, therefore, c must be 0. So, that means we have got our v equal to 3 divided by pi sin 30 by pi. Once more we apply the same method. So, v is again ds by dt, and we see that if I take y, or that is s here, it is really s, which is write as y here. So, if I take that function as y, new function, which is minus cosine 3t by pi, then its derivative is equal to 3 by pi sin 3t by pi. That is clear, minus cosine 3t by pi. So, you differentiate, it gives sin 3t by pi times 3t by pi with respect to t, that gives 3 by pi. So, it is v. So, that means y prime equal to v, where y equal to this. Therefore, y can differ from s by a constant. So, s must be equal to y plus k for some constant k. Now, we apply the condition s at 0 equal to 1. So, that gives y, which is this one, minus cosine 3t by pi, evaluate that at 0, that gives minus cosine 0, which is 1 minus 1 really. So, this is minus 1 and plus k should be equal to 1, s 0 equal to 1. So, that gives k equal to 2. So, we get our s as minus 2 cosine 3t by pi. Fine. So, twice we have to apply the same method, starting from acceleration to the displacement. Okay. So, let us take the next problem. Here there is some function, assumed that there is a function which is defined on its domain to real numbers, such that f prime of x equal to square root of x minus x secant square x. We are given information on f prime, and also we are given f of 0 equal to 2. So, find the value of f of 2. It is similar to the earlier problem. Here derivative is given. So, that means you have to guess some function whose derivative will be square root of x minus secant square x. That should be our starting point. So, we start with this, because we know if you take root x, that will come from 3 by 2, right. So, if I take x to the power 3 by 2 and differentiate, we would get 3 by 2 x to the power 3 by 2 derivative will be 3 by 2 x to the power 3 by 2 minus 1, which is half. So, since I have only x to the power half, not this constant, so I multiply this constant here. So, I start with g x equal to 2 by 3 x to the power 3 by 2, and secant square x comes from tan x when you differentiate. So, we start g x equal to this. So, this is a guesswork to find out this g, whose derivative should be equal to that which is given. Now, we find that g prime x is equal to 2 by 3 times 3 by 2 into x to the power half minus secant square x, which is f prime x. So, g prime x matches with f x. Therefore, we conclude that g x and f x will differ by a constant. So, we say that f of x is equal to g x plus c for a constant c. Then we use the condition f at 2, okay, and we have to find f at 2. We have to use the condition f of 0 equal to 2. So, now when you substitute 0, f of 0 equal to 2 gives g of 0 plus constant, and we evaluate g of 0. G we have guessed. So, at 0, first one is 0, second one is 0, g 0 equal to 0, right. So, left side gives c, right side 2. So, c is equal to 2. Therefore, our f of x is equal to g x plus 2, which is this. So, once f x is obtained, we evaluated it at x equal to 2 to get our answer, because we are interested in finding the value of f of 2. So, when you substitute x equal to 2, it is 2 by 3, 2 to the power 3 by 2 minus tan 2 plus 2, and that is the answer. Okay. So, let us look at the next problem. Suppose a and b are two real numbers. We want to show that the absolute value of sin b minus sin a is less than or equal to absolute value of b minus a. So, it is not just sin of x is less than or equal to x, or absolute value of sin x is less than or equal to absolute value of x, but b is coming from the argument of that function sin. So, this is what we want to show. Okay. So, first thing is we notice that if a is equal to b, because they are any real numbers, they can be equal. If they are equal, then sin b equal to sin a, b is equal to on the other side. So, 0 less than or equal to 0, there is nothing to prove. So, assume that a is less than b, one of them is less than the other, say without loss of generality, assume that a is less than b. Okay. So, now consider the function f x equal to sin x on this closed interval a b. Why this closed interval? Because this one is f b minus f a and the other side is b minus a. So, we think we can apply mean value theorem. Okay. So, consider f x equal to sin x on the closed interval a b. Then it is continuous on closed interval a b and differentiable on the open interval a b. So, by mean value theorem, there exists one c inside the open interval a b in between a and b, such that f b minus f a is equal to f prime c into b minus a. But what is f prime c? F x equal to sin x. So, f prime at c is cosine c and its absolute value is bounded by 1. Therefore, sin b minus sin absolute value is less than or equal to mod cos c mod b minus a. Mod cos c is less than or equal to 1 for any c. Therefore, this is less than or equal to mod b minus a. So, the same thing also holds for cosine. As for sine, you can continue the same way, because its derivative will be sine, which will be again bounded by 1. Okay. So, let us consider the next problem. Here we are given with a quadratic, it is a polynomial of degree 2. So, p x square plus q x plus r. So, it is defined on everywhere, it is defined. So, we are considering this function as a function with the domain a b. So, here of course, we assume a is less than b, right, and it is given that this coefficient of x square is not 0, p is not 0. So, that the C in the mean value theorem is unique. So, what is the meaning of C in the mean value theorem? We know that if you apply the mean value theorem, if it is at all applicable, its conclusion will be f of b minus f of a by b minus a equal to f prime c for some c between a and b. So, that c, we are asked to say that we are asked to show that this c in between a and b is unique. There cannot be two different c's satisfying the same condition if it is a quadratic with p not equal to 0. Okay. So, suppose on the contrary that there are 2 points, we want to show only uniqueness. There exists a point because mean value theorem guarantees it. It satisfies because this is a continuous function on open interval a b, differentiable on open interval a b and continuous on closed interval a b. So, mean value theorem gives a c at least. So, suppose there are 2 points c and d, then f b minus f a equal to f prime c into b minus a and f b minus f a equal to f prime d into b minus a, right, both are satisfied. So, since we are assuming that b is greater than a and f b minus f a same on both the sides. So, by dividing this we say that f prime c equal to f prime at d, both the things are same evaluated at c. But what is f prime? F prime of course, you can find out from there, which will be 2 p x plus q, this is your f prime. So, this evaluated at c is equal to this evaluated at d, that is given. Now, you consider the function f prime itself. So, this has the condition now f prime c equal to f prime d and it is again differentiable, as you can see it is a linear function or rather linear polynomial 2 p x plus q. So, its derivative also exists inside the open interval a b. You need of course, inside open interval c d only, c and d can be in between a and b, not necessarily whole of a b. So, it is differentiable. Then you can apply Rolle's theorem to conclude that f double prime alpha must be equal to 0 for some alpha between c and d. So, if alpha is in between c and d, it is also between a and b. So, there is one alpha between a and b such that f double prime alpha equal to 0. But f double prime is equal to 2 p, right, it was 2 p x plus q. When you differentiate it again, it is a constant. So, that goes away and this x also goes, you get 2 p, f double prime x equal to 2 p. Since p is not equal to 0, 2 p is not equal to 0. So, f double prime x is never equal to 0 inside the interval a b. So, it contradicts our conclusion that f double prime alpha equal to 0, which we obtained by Rolle's theorem. So, that means there is something wrong. So, what is the wrong thing? Our extra assumption that between a and b there are 2 points, at least 2 points c and d, that is wrong. Therefore, c in the mean value theorem is unique. Okay. So, we consider next another problem where we have a function f of x given as 1 minus x to the power 2 by 3. Now, you see whether it is defined on the interval minus 1 to 1? Yes, it is. So, consider this function f, which is defined from minus 1 closed interval to r given by f x equal to 1 minus x to the power 2 by 3. Now, if you differentiate it, you would get 2 by 3 into x to the power minus 1 by 3 with negative sign, 1 becomes 0. So, this is correct, f prime x is equal to minus 2 by 3 x to the power minus 1 by 3, that is its derivative. Now, you see f at minus 1. So, if you substitute minus 1 here, so this gives minus 1 square which is 1, 1 minus 1 is 0 and f of 1 is 1 minus 1, that is also 0. So, both f of minus 1 and f of 1 vanish. So, if you think of Rolle's theorem, or even mean values theorem, it should say that f prime x should be equal to 0 for some x in between minus 1 to 1. However, if you take f prime x, which is minus 2 by 3 x to the power minus 1 by 3, it is not equal to 0 on minus 1 to 1. Why do you say it is not equal to 0? At 0, it is not defined, right. So, you cannot say f prime x equal to 0 on minus 1 to 1. Why? The reason is simple. We say that Rolle's theorem is not applicable, because f x is not differentiable in the open interval minus 1 to 1. Because at 0 f is not differentiable, right. F is not differentiable at x equal to 0. So, that you can see how it holds. So, therefore, f x is not differentiable on minus 1 to 1 open interval. So, we cannot apply Rolle's theorem. I think we stop here.